I drove back this morning on campus, it brought back a lot of good memories. But of course, there are also many new things. In fact, this building is new, so I haven't been in this building. So yeah, it's great. So okay, yeah. I believe there are many old buildings, but this one is definitely new to me. Okay, so as you can see, the top of my title is actually like a double title here. Originally, I thought about talking about federated multi-objective learning. In fact, I have a typo. I should put a learning there. But later on, when I thought about it, I actually wanted to talk a little bit more about our recent work on democratizing LLM with the edge. But of course, federated learning will play a major role in this project. Yeah, in fact, I'm also the managing director of AI Edge, as Hong already mentioned. It's one of those $20 million AI institutes funded by NSF. So we started in 2021. Okay, so we're actually the second cohort of all these AI institutes, and this is our ecosystem. So you can see our AI institutes have 11 major research universities. We also have 2 expand AI schools recently, and we work extensively with lots of companies, and we also collaborate closely with DARPA and also all the DoD research labs. Of course, we are overseen by NSF, and we also partly funded by DHS, Department of Homeland Security. And of course, the headquarters is right at Ohio State. Okay, yeah, so these folks are faculty investigators. There are too many, so I won't read through their names one by one, but you will see lots of colleagues and friends. They are all very well known in the community. I'm right there. So yeah, we also work closely with the DoD and the industry. So these are some of the folks, and yeah, this is our management structure. Our AI Institute director is Professor Nesh Shroff. I'm playing the role of managing director, so I kind of have the responsibility to kind of advertise ourselves a little bit in here. So we have 8 research thrusts. So roughly speaking, the 4 thrusts, number 1 to number 4, are called AI for networks, and the thrusts 5 to thrust 8 are called AI on networks. So later on, I'll show you a little bit what it means. And so when we started out, we have 3 use cases, but later on, we actually consolidate many things, and we actually now focus on 4 so-called end-to-end problems. So the goal here is trying to show to NSF and the community that the sum, right, the whole thing is more than the sum of the parts, right? So, and also we have many other activities on broadening participation and education, and also collaboration with the DoD and industry. Okay. So lately, we also go international. This is our original structure, with AI for networks and AI on networks. But lately, we also started to collaborate extensively with lots of international universities. So these are the new research tasks added on top of our original proposed research tasks. And these are our, international collaborators started last year, and this year we also added 2 more. Okay. So these are our international collaborators. So there are too many, so I won't read through all of them. Okay. So as I already mentioned, so earlier, let me go back a little bit. So we have 4 end-to-end problems. So yeah, here I don't have the space to show the title of these problems. I'm personally leading this one. This is democratizing LLM with the edge. But we also have several others. So this first end-to-end problem is on using AI and machine learning to configure, large-scale cellular networks. So this is actually being implemented on AT&T's cellular networks. So it's led by Professor Sanjay Shakotai at UT Austin. And the second one is on using ORAN, ORAN-enabled AI-powered resource allocation in wireless networks. This one is led by Professor Elisa Bettino at Purdue. And the last one is on, massive scale, city scale distributed inference. It was led by Stratis Ioannidis at Northeastern. So I'm leading the third one, which is something I'm going to focus on today. All right, so let me switch gear to this end-to-end problem on democratizing LLM with the edge. So you can see this effort has 29 researchers, and with 27 of them spanning across 6 universities and 2 volunteering from the industry. Okay, so yeah, it's truly a very huge team effort. So the history about this project is actually quite interesting. So AI Edge started out in 2021. Okay, kind of roughly at this time in 2021, and then not long after, as we all know, right, ChatGPT came out and took the world by storm, and then make a big bang. And then basically after ChatGPT, the landscape of AI research has changed dramatically. Right, this presents a lot of challenges, but also a lot of great opportunities. So as we all know, right, so when ChatGPT first came out, Microsoft has already built a huge supercomputer, consists of tens of thousands of NVIDIA GPUs interconnected by these super high-speed infinite band connectivity, right? And actually, as of today, right, so basically you can see, these are the shipments of NVIDIA GPUs to all these major big tech companies. And so these are different stats from different sources. But you can see Microsoft and Meta have the largest share. And not surprisingly, the largest frontier models like GPT-5 and Llama 5 or Llama 4. So these largest frontier models are all hosted and trained by these big tech companies, right? And Microsoft and Meta AI. So these huge kind of training with a massive scale, compute data center actually lead to a lot of concerns. One concern is that, due to this non-transparency, right, we don't have access to these state-of-the-art LLM technologies. And because of that, security and trustworthiness also becomes a very big concern. And meanwhile, these kind of huge data and compute centers lead to a lot of environmental sustainability concerns. Okay, so here we ask the following question. In fact, all these also put our academic researcher at a disadvantage, right? We don't have these kind of a compute and data resource. So we asked the following question: can we open LLM training and distributed and network environment? Okay, or in other words, can we enable LLM training to anywhere and everywhere? Okay, so that's our overarching question we want to answer. Well, of course, at AI Edge, we have the following vision. We believe that we can democratize LLM training with the edge. Okay? So as we all know, LLM training contains pre-training and fine-tuning. So in pre-training, you are just using a lot of human natural language data unlabeled, right? And to do this kind of next token prediction until the model can spit out something smoothly. And then after that, you use some small high-quality data set to do the fine-tuning, right? Or basically allow the model to perform some specific natural language tasks like doing summary or a sentiment analysis or question answering or doing some alignment, right? So that the model can produce something aligned with human values, something like that, right? So our vision is that actually we don't have to rely on the huge data and computer center to do these things. We can actually come up with a unified learning framework in this broadly defined edge. So here we basically view everything outside of a huge data and compute center as the edge, okay, as like a broadly defined edge, not necessarily wireless edge. All right, so now the key idea is that In fact, if you look at different universities, right, even though none of us can rival all these big tech companies in terms of compute and data resources, but collectively we do have something interesting, right? So, for example, this year at Ohio State, we invested 120 H100, okay, and also we know that UT Austin recently bought at least 500 H100. And not long after, I heard that Texas A&M outrivaled them by buying another 700, something like that. Okay? So if you pull these resources together, you can see that we do have some compute resources, right? So we're thinking, is there a way in which we can, help them, pull these resources together and do something, more interesting, right? Now, of course, the answer is yes, and we are trying to do that. But to achieve this kind of overarching goal, there are also lots of challenges, right? So the first thing is that in pre-training, right? If we want to enable this kind of distributed training over the public network, we need to handle a lot of network delays, data losses, right? How you can transmit data over a limited bandwidth, and in fine-tuning part, sometimes we are also thinking about can we leverage your devices in office, at homes, and also connected through wireless to do fine-tuning. Later on, I'm going to show you some demos like that. Okay? All right, so need to deal with all these challenges. So let me talk a little bit about the first one, which is on distributed pre-training. So started in last year, which is our year 3, we built this kind of cross-institution pre-training system across Ohio State and Wisconsin. Okay? And so let me show you how this system looks like. So here we actually have 3 clusters. This cluster is actually my cluster at OSU with 4 H100. And we also enlisted 2 clusters from Wisconsin, owned by Professor Rob Nowak. So he actually had owned 2 clusters, one with 8 H100, and the other one is for 3090. So 3090 is, if you know, these are actually not for AI. Okay, just these are for gaming. So these GPU, so these are much lower end GPU. The A100 is relatively more powerful. Of course, H100 was like the top end GPU last year, but now it's no longer in production. Okay, now it's H200. Yeah, so when we build a system, we also we ran into a lot of challenges. So the first challenge is that the communication between here we use a AWS server as the parameter server. So the whole architecture is pretty much like a federated learning system. Okay, and in fact, in each cluster, we use this FSDP to chop the model into multiple pieces so that a large language model can be hosted on these clusters, and then we designate one GPU as the master GPU and talk to AWS server. Okay, and in fact, that AWS EC2 server is situated at Ohio State. Okay, so now when we implement all these things, we realize that one of the immediate challenges is that there's a lot of communication imbalance. Since this AWS server is closer to our cluster, so the communication latency from Wisconsin to that server is much longer than that with OSU. Okay. Now, of course, the idea here is that we can do some compression, which I'm going to touch upon later, and also we will do something called multi-server balancing to kind of deal with the communication heterogeneity. All right, so basically this is how it works. If you are familiar with federated learning, this is pretty much federated learning. Okay, so here we have this client and a server, right, a parameter server, and so the system will be initiated by one of the clients, and then the clients will send the parameters to the server, and the server will distribute all these initialized parameters to some other clients, and And then basically, so after you start the training, you're just doing federated learning, and then the model is synchronized every 10 minutes. So why we spend 10 minutes to synchronize this? That's because LLM is huge. Okay, so the communication latency is large. So we actually, last year, this is the model from the version from last year, so we need to synchronize every 10 minutes. And sometimes, with all these distributed training, right, things are not that reliable. Some clients can fail, right? So we need to come up with some fault tolerance mechanism to deal with it. And then, we want to be able to relaunch the client and start from where we left off, right? And then we continue training. So that's basically how the system works. Okay? So as I said, there's a lot of communication heterogeneity, right? So, for example, earlier I mentioned the latency from Wisconsin is much larger than the latency at Ohio State. So here we propose the following idea. We leverage this so-called VPC, virtual private cloud, to allocate different servers to cover different areas. So this is actually our system this year. This year we actually expanded one more school. This is at UT Austin with another cluster from Professor Sanjay Shekhatai's group. So here, with this architecture, we are able to implement this sort of like a multi-server architecture with the ring all reduce connecting all of them. And the nice thing about this kind of system is that it allows us to, perform very frequent gRPC communication between all these servers. And also, with this ring all reduce architecture, we will not suffer like single server communication bottleneck. Okay, and this is how we deal with the communication heterogeneity. And it also gives us a lot of benefit in protecting privacy and security, okay, because of this kind of a virtual private cloud architecture. Another idea we want to deal with the huge communication latency is compression. Okay, so in fact, this compression idea is also quite interesting and novel. If you look at the literature, most companies, most research works are talking about, quantization. So here we actually have this kind of two-level data compression idea. So on top of compression, we also add another coding on top of it to further extract more compression gain. Now here, of course, the coding can be any compression efficient coding, but later in our demo, we just used the Huffman coding, which is probably the most well-known lossless data compression scheme you can think of, right? So this is how it looks in our demo. So here, interestingly, David Huffman is an alumni at Ohio State. Okay, but anyway, so here this is the payload. This is the language model. You have lots of huge tensors, and then after we do a compression, we basically flatten the huge language model into some a quantized vector. Okay, and then we will send the Huffman coding tree along with the quantized vector to the receiver for reconstruction, and then the payload will be sent, and then the receiver will get this hugely compressed model. Okay. Now the decoding process is also the reverse process. So essentially, with that you decode and reconstruct your language model at the receiver end. All right. So now let me give you a quick demo. This is our latest. Yeah, this is a demo between OSU and UT Austin. So these are all the detailed configurations. So I don't have time to read through all of them. So this screenshot shows how the system is started. We have two servers, right? As I already mentioned, we have two parameter server in a virtual private cloud. This is one of the OSU workers. Yeah, the video is sped up a little bit. Okay, so you can see how the system is initiated and the training gets started. Okay, now here is a real-time pre-training progress. We actually developed a pretty sophisticated real-time dashboard to monitor the pre-training process. So here we can see, let me pause a little bit. So you can see, we can monitor in real time how many data has been sent and received. What's the latest round trip time? RTT. Basically, the round trip time is an indicator of what's the current network congestion situation. We can also monitor, per round or on average, right? How many training each university have contributed. And we can also monitor, these are the memory consumption. This is how the overall, the training loss and validation loss will converge, right? So yeah, all these very useful information. And then actually during the training process, one of the GPUs at OSU fell. And then actually the system can recover and picked up where we left off after this node reboot by itself, and then also UTL rejoins the whole process, and the training continues. Okay. So here are some like a snapshot of the training outcome. This is actually at the beginning when you started the pre-training, right? Here we asked the model by giving a prompt. It's too hard to see, maybe too small. So once upon a time, right? Then you can see basically the model just generated some garbage at the beginning, right? 20 minutes into the pre-training, it's not doing much. Okay. Now after 1 hour, it's still not very good. It just keep repeating some nonsensible words. But this is actually after 10 hours, which is not too long, right? After 10 hours, you can, maybe it's hard to see from the back, but I can actually read a little bit for you. Right? So this is a prompt, once upon a time. And then it says, 5th century AD, a giant mummy found in a cave in the village of Ciceros, I don't know where it is, was discovered. The mummy was found to be a skeleton of a gigantic mummy or something like that. Okay, so it still doesn't make too much sense, but you can see the language is actually quite smooth, and it's getting closer and closer to natural human language. Okay, this is another training about after 40 hours, so less than 2 days. So yeah, again, it's too hard to see, from the back. But basically, if you read through the text, you'll see that the story now becomes much smoother. Okay, but of course, if you really process the story, it doesn't make too much sense because in pre-training, the model is just doing like a next token prediction, right? It's not really doing something useful. So that means that we need to do fine tuning to make it to generate something useful. Okay, so this naturally leads to the next thing I want to talk about, which is the fine tuning. Okay, so in fine tuning, basically you have a pre-trained LLM model already, right? You want to use some custom data set and fine tune it for some specific use cases. So last year when we started this, we actually implemented this kind of quite a few fine-tuning methods on this famous Coliseum simulation platform at Northeastern. Okay, some of you may know that this is basically Coliseum is a huge supercomputer that can emulate all sorts of wireless communication channels. Right? All right. So yeah, this is how it looks. So here, this is the Coliseum SRN cluster. As I said, it's a huge supercomputer, and I believe Coliseum started out by DARPA, right? And somehow, eventually, it's owned by Northeastern. And so here we created a wireless networks, simulated wireless network. So we have several clients on some sort of software radio nodes, and we also allocate another SRN as a server. And then initially we used some PyTorch protocol to establish this network. There are some benefits, however, there are also some issues. And the issue is that all these nodes are actually not that well equipped with GPU resources, so that they are not capable of doing useful fine tuning. Okay. Now, interestingly, at Coliseum, they do have a GPU cluster, okay? And in fact, the GPU cluster is H100, it's pretty high end. However, the problem is that for some unknown reason, on Coliseum, the GPU cluster doesn't talk to the SRN cluster, okay? So eventually, we're not able to use that directly. So actually, we come up with another idea. We kind of hack into the Coliseum system. and actually build like a gRPC tunnel across these clients and this SRN cluster. And then we use these SRN nodes as a router node, okay, so that all the fine-tuning computation is offloaded to this GPU cluster. That actually takes quite a lot of work to do last year. But coincidentally, after we finished the project and looking back, we realized that actually this is exactly like a federated learning system and share the same architecture as we did earlier. Okay? So in some sense, we kind of went to the moon and then we rediscovered the Earth, something like that. So eventually we were so happy that both the pre-training and fine-tuning share the unifying framework and can do both things simultaneously. All right. So this year we actually put this system on a real network. So if you remember earlier, we have several clusters at OSU, Wisconsin, and UT Austin. In fact, this year we also bring in IIT Madras from India. So this is truly an international fine-tuning system. Yeah. So here we tested several fine-tuning methods, but I don't have the time to go through all of them. I just want to point out two. So this one is called hybrid LoRa. So here, if you know something about federated learning, so in this kind of hybrid LoRa-based federated learning, you have some low-rank parameters called AB. Okay, you want to tune. So here in this method, by the way, so all these fine-tuning methods are our own research work. Okay, so in this work, it's actually one of the papers we published. We have two sets of parameters. So these A's and B's are still the low-rank parameters. This U is like a public parameters. So the motivation is that some of the parameters could be private, right? So when you fine-tune a model, you may not want to share your low-rank update parameters. So these U's are some publicly shareable model parameters you can share with the server, right? So by doing this, the the privacy will be preserved. However, this kind of method may, the limitation is that this U sometimes could still be pretty large. So in some sense, the communication may not be that efficient, right? So this is okay. So another idea we try is that for all these large language model, if you do federated learning, right? So one of the primary assumptions is that the models can be fit into each client. However, with this kind of a huge LLM, this may not be true all the time. So our idea is that we can split the model into two parts. Okay, so one part is handled and trained by the fine-tuned by the client, and another part is fine-tuned by the server. Okay. However, if just do this naive split learning, there's some limitations as well. The reason is that when you do this kind of split learning, the server will get into the back propagation process, and this will become a sequential process, will slow down and lose the benefits of data parallelism in federated learning. Right. So we do have some ideas. We call an auxiliary model and and alignment, to fix these things. So, but due to the interest of time, I won't talk about getting into those details. But I can happily share with you offline how we did that. All right. So again, this is like a demonstration. This is our this year's demo, like across 4 sites internationally. Okay. Okay. Yeah. So this is how the system looks like. We have 4 clusters. Again, we leverage multiple AWS server as the the server and the model and stuff like that. Okay. Here, this one shows how we initiate the parameter server. Actually, that workers is at IIT Madras. This one is at Ohio State. Okay. Again, some screenshot to highlight how things are initiated. All right, so this one is the real-time fine-tuning process. This one is with the hybrid LoRa method, right? We can see in real time. Again, let me pause a little bit. So we can monitor how many data we receive and send. We can actually also monitor how much contributions, right, from each university, and in terms of the compute. And these are the round trip time, right, indicating the real time network congestion and channel conditions, something like that. Okay, and yeah, so this is also showing the the latency distribution, and also that part is the validation loss and things like that. Okay, so also we can in real time monitor these metric like called exact match or F1 score. These are indicating your fine tuning quality of the language model. Yeah, you can see, yeah, these are like a real-time contribution from each side. Okay. It's a little bit long, I think. Yeah, this one is also the real-time progress of a split learning, right? Yeah, the dashboard interface like this, so we can also monitor how many data we receive and send. What's the GPU utilization at each site? So this one is basically a monitor of how these the auxiliary model that I mentioned, how they are aligned at different time. So we can still recover the data parallelism benefit in federated learning. And we also, in real time, monitor all these, fine-tuning quality metrics. Okay, so we know how well these models are fine-tuned. Okay, so yeah, again, so these are just a glimpse of other fine-tuning methods. Besides those two I mentioned, we also have something called Raven and zero-order methods. So all these are our research work at AI Edge at by different researchers, and all these are also, all published in major machine learning conferences. All right, so some fine-tuning outcome, okay? So here we just do a very simple question and answer. So we grab a paragraph from our AI Edge website, okay, and ask the model some question related to this paragraph. So question one is, like, what's the institute goal in combining network and AI? So all these fine-tuning methods can spit out roughly the same answer, okay, even though they may not produce exactly the same answer, but all these answers are related and correct, okay? And question two is like, what quality should the next generation of edge network, right, something like that. You can see all the fine-tuning methods produce the same outcome, same result. So these are all correct. Question three is, what's the transformative application, blah, 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 right? And then again, you can see the answers are all correct and yeah, related to this paragraph. Okay. All right, so yeah, that basically wraps up the demo. Okay, so in summary, our goal here is to democratize LLM with the edge, and we have what we have achieved is that we have the same unified learning framework for both pre-training and fine-tuning, and yeah, so as a proof of concept, we verified that it's indeed feasible to do pre-training and fine-tuning on the edge. Okay. So the final takeaway is that all these innovations at our institute leads to the first what I call anywhere and everywhere LLM training and pre-training and fine-tuning. Okay, so these are the roadmaps. In our previous 3 years, we have developed all these theoretical foundations, and last year we started to build this distributed pre-training and fine-tuning system. Year four is this year's our year four. We have expanded the system and to add in compression, all these kind of different types of fine-tuning tasks. And next year, we're going to continue this effort to test and verify all these communication efficient machine learning methods at the edge, right, developed by all our AI Edge researchers. We will also focus very much on security and privacy next year. Yeah, so after year 5, that basically is that's the end of our AI Institute, and hopefully we'll get renewed in the future. Okay, so that wraps up my presentation. Thanks. Yeah.
We do have maybe a few.
Sure. Yes.
So thank you for the presentation. I find it like really interesting and inspiring. So my question is more about like you are probably like envisioning this to run on the edge, right?
Yeah.
And I find it like really interesting, like the way that you prove that it's possible to do this kind of distributed training, so to say. So my question is. So this fine-tuning, the way you measure like the accuracy of the model, shouldn't be like tailored to whatever the purpose of that model should be like. My point is like not use the model just as a, let's say, long-term memory, but something which needs to reason, for example, with external resources like MCP, for example. And how do you prove like the reasoning, like reasoning model, for example, like if it does the reasoning correctly and not just the right answer? So like your takes on that?
Yeah. So as I already mentioned, right? So we do have like a very systematic way to measure the fine-tuning quality, this kind of like a F1 score or exact match. These are the like a well-accepted benchmark metrics in the NLP literature to measure how good these fine-tuned models are, right? Now, of course, just looking at this number doesn't give you too much information. So that's why in the end, we show a few examples, right? Some anecdotal examples to see how well the fine-tuned model will work, right? But of course, a more systematic way and a more, a more systematic way to measure the fine-tuning quality would be using some of these metrics people develop. This is actually for these are for question answering. For some other more sophisticated fine-tuning tasks like alignment, that also requires some other metrics to measure. So yeah, but different fine-tuning tasks may have different ways to measure the quality.
And another quick too, like one is like what are the network or the network requirements if we want to move this scheme to from some let's say environment where the links, the network links are not like optical fiber, but something like more wireless like. What would be your take on that? Like what are the really it needs to be like the reliability of a optical fiber, super high bandwidth and so on.
So yeah, I'm not sure if I understand question. So basically, we're trying to enable, right, to democratize LLM training, to the public with the edge network. So
yeah, let me rephrase it. Like, imagine that you want to, let's say, borrow your GPUs to something which is on the space, and the only access that you have is not a super nice optical fiber, but you have like something more messy, like a wireless link. That would be possible. Like in reality, what's the feasibility of that?
Right, that's possible. In fact, the very first fine-tuning system we started last year, like this one. This, even though it's not a real wireless network, but it's closely simulating wireless networks. We actually leverage this coalescing system to try different wireless channels. Yeah, of course, this also depends on how large that language model is, right? And what kind of data set, lots of different factors. So in this kind of environment, last year, we were able to train some GPT-2 model, roughly like 300 million parameters, things like that. Not a huge, really frontier model, but still you can show that, by using a wireless networks, with a couple of hours, you can fine-tune these things to do very useful tasks.
No, very, very interesting. But it's like even if it's not like super model, maybe for the task that you wanted, it's enough. So that was also really to my question of what's the purpose of the fine-tuning. So if my model is going to handle just some basic robot movements, that could be enough.
Yeah. So in fact, it doesn't have. I mean, this type of a training algorithm doesn't have to be used for LLM. So in fact, any large foundation model, as long as you have some pre-training, fine-tuning pipeline, right? So all these methods are applicable. Yeah. So maybe like for example, at era, if you have some application, right, where you're trying to build a foundation model and then fine tune it for different specific tasks or use cases in ag, right, then these kind of methods can still be used.
Okay, and just the last one, because this topic is really interesting to me. And like, I don't know if you're aware of this kind of training-free efficiency methods, like, sparsity, like playing with the sparsity, playing with quantization, pruning. You think that could be applied to your actual work somehow? Thanks.
Yeah, I'm aware of some of those, but we haven't really touched upon these things yet. But I think that's interesting. Yeah, I think we should put some thoughts to it. Yes. So. Yeah.
Great.
Yeah.
Thanks, Kevin. I do have a question for you, but I'm going to save that for probably after I'll catch up.
Yeah, sounds good.